Welcome back. In this video, we're going to take a look at a scenario involving the transfer of heat between various objects. And we're going to use a connection between the amount of heat an object takes up and how much its temperature may change. And this connection is given by a quantity known as the heat capacity. Go ahead and take a look at the problem statement. So in this problem, we have a copper bowl full of water. The copper bowl and the water are both at 20 degrees Celsius initially. And then a copper cylinder is dropped into the water, and this copper cylinder is very hot. Once it's dropped in, temperature starts to change, and then after a little bit of time, everything equilibrates to 100 degrees Celsius. And then also it tells us that during that process, some of the water has been boiled off to steam. The question asks us to find out how much energy is given to the water as heat, how much energy is given to the bowl as heat, and then also find out the original temperature of the copper cylinder that was dropped into the water. For this problem to get started, we're going to use one fact which is stated in the problem, which is that the system itself, all this, these three objects together, are isolated from their environment. Because they're isolated, that means that the internal energy of this full system does not change. So we write that as the change of the internal energy is 0. In other words, the internal energy now and a little while later, and then later it's going to be the same quantity, whatever it is. The reason this is useful is because we can relate this to two quantities by the first law of thermodynamics. And these quantities are heat and work. So the first law says that the change in internal energy equals however much heat you put into that system minus however much work the system does. The good thing is for these types of problems where we deal with solids and liquids, they don't do any work because work arises when you can compress and expand objects. And solids and liquids do not really compress or expand. So we only deal with energy changes given by heat transfers. So we're going to not have to worry about that because the volumes don't change. So basically what we have here is a situation in which no heat is given to this system, but among the components themselves, they can transfer heat to one another. So this full heat given to the system, we can write it as the heat transferred to either one of these three objects. The heat transferred to the water, or the heat transferred to the bowl, or the heat transferred to the copper cylinder. Because they add up to 0, if this is positive, one of these guys has to be negative. In other words, if heat is given to the water, it must come out of the bowl, or it must come out of the copper cylinder, etc. The question asks us to find out what these values are. But since we don't know any of them, it looks like we have one equation with a bunch of unknowns. We do have a bunch of temperature changes, though. So what we're going to use is the fact that heat and temperature changes are connected by this quantity called the specific heat capacity. And that's quantified in this equation, where C is the specific heat capacity and M is the mass of the object, and T is how much a temperature changes. So what this means is that if you put in heat into an object, its temperature will change depending on how big its heat capacity is. As an example, the heat capacity of water is about 4.187 joules per gram per Kelvin. Now what this means is the following. It means that for every gram, for every temperature degree Kelvin you want to raise it, you have to add in 4.187 joules. This is actually a pretty big number. As a comparison, the heat capacity for copper is only 0.380 joules per gram per Kelvin. Okay, let me explain these kind of in a physical sense, why these kind of make sense, why one is 10 times bigger than the other one. Imagine heating up some water on a stove. As you have the flame going, if it's on a gas stove, it takes a while for the water to heat up, but the pan heats up right away. The pan has a much smaller heat capacity. That means that if you want to raise it by a few degrees Kelvin or Celsius, because this is small, it only takes a little bit of heat to do that. That's why the pan heats up so quickly, because it has a small heat capacity. On the other hand, the water inside the pan takes quite a while to heat up. Its heat capacity is quite large. So if you want to raise it by some degrees, whatever number of degrees, because this is so big, it takes a lot of heat to do so. And so you see that these guys are connected, the heat and the temperature, but how effectively the temperature can change based on how much heat you put into it depends on its heat capacity. Now we can use this equation to find out the energy given to these objects as heat. But before doing that, there's actually one more way you can, physical process that can happen when you transfer heat to an object. The temperature So you see that the heat changes the temperature, and the temperature just means how much the molecules are vibrating. However, you can also get something else to happen. If you add heat to an object, you can get it to melt or to kind of burn off as steam, to vaporize. And we can write this in the following way. Heat can also be given to change its phase. So you change it from a solid to a liquid to a solid, or a liquid to a gas, or a gas to a liquid. How much heat it takes to do so is given by this quantity called the heat of vaporization, or the heat of fusion. For water, that quantity is 2256 joules per gram, and then for copper, that quantity is 4730 joules per gram. What this means is the following. In the first case, you add heat to an object and you get its temperature to rise. That just means the molecules are vibrating faster and faster. At some point, if you add more energy to it or more heat to it, the molecules don't start vibrating faster. In fact, they break apart. The bonds between them break. How much energy it takes to break them apart is given by this, the heat of vaporization or the heat of fusion. So this is the energy or the heat needed to change temperature. This is the energy or heat needed to change phase. We see in our situation we have both of these things going on. We have the temperature rising from 20 to 100 degrees Celsius, but also some of it changes phase from liquid to gas. So we're going to have to consider both of those. Let's go ahead and answer the first part of the question. It says how much energy is taken up by the water as heat. So I'll write down QW, which is what we're looking for here. How much energy is given to the water. It's going to rise from two different aspects. The heat's given to change its temperature from 20 to 100 degrees. Okay, and that's going to be determined by its heat capacity. Once we get to 100 degrees, because it boils off at 100 degrees, its boiling point is 100 degrees Celsius, 5 grams of it is actually going to be converted from water now to steam, and that's going to take some energy. So we're going to have to add some more heat to change it from a liquid to a gas. Not all of it, but just some of it. Okay. Now let's write this out in terms of the two formulas we have given here. The first formula says that the heat taken to change its temperature is given by its heat capacity times its change in temperature. And the second formula says that it's the heat given to change 5 grams of it from liquid to steam is given by the heat of vaporization times its mass. But we're only going to change 5 grams of it, so I'm just going to put 5 grams here, not the full MW. And finally, we have the temperature here is TF minus TI. And it looks like we have all these quantities, so you can actually plug everything in. This is 4.187. We have the mass, which is 220 grams. This is in per grams, and that's in grams, so the units work out there. We have the final temperature is 100. The initial temperature is 20. We can plug that in. This guy we have here, and then the 5 grams we have. So plugging all those numbers in, you find out that the amount of heat taken to make this process occur is about 84.97 kilojoules. Okay? And again, that arose from two processes. One is changing the temperature up to 100 degrees, and then one is boiling off a little bit of that water to steam, changing its phase. The next part of the problem is very similar, so why don't I let you take a crack at that, and then we'll come back and look at number 2, and then we'll finish up with number 3. Second part of the problem is very similar to the first part. We're looking for the heat taken up by the bowl, and again, it's going to be coming from the fact that its temperature is rising from 20 to 100 degrees Celsius. It doesn't change phase, it just remains a solid bowl, so the second term will not be there. So this is actually a little easier than the previous one. We're going to use the heat capacity of copper, of the copper bowl, times its mass, times its change in temperature. In this case, the heat capacity of the bowl is made out of copper, so we have 0.380. Its mass is 150 grams, and its temperature change is 80 degrees. One thing I forgot to point out in the last part of the problem is that you notice that the temperatures here are given in Celsius, but this heat capacity is given in Kelvin. And I didn't account for that. That's fine because Kelvin and Celsius are related by a shift. You just add 273 degrees to Celsius to get Kelvin. So when you subtract Celsius degrees, if you added 273 to both of these, that 273 would cancel out. So you don't have to worry about it. So if it's in Kelvin and Celsius, you can treat them the same in this problem. And then plugging those values in, we find a total heat absorption of the copper bowl of 4.56 kilojoules. Now, comparing these numbers, we see this kind of makes sense with our intuition. This number is 20 times bigger than this number. And that makes sense because the copper bowl has a much smaller heat capacity. Mass also matters, but their masses are not that much different. They're between maybe about a factor and a half, 1.5 times. This difference is 20 times though. So even though the masses are a little different, that shouldn't make much of the difference. The difference is the heat capacity. The copper bowl has a much smaller heat capacity, so it takes a smaller amount of heat to change it from 20 to 100 degrees. Whereas the water, it has a much bigger heat capacity, so it takes 85 kilojoules to change it 80 degrees. Finally, let's finish up the problem. The last part asks us to find the original temperature of the copper, and for this we can use this equation. All the heats have to add up to 0. We know these two heats, so we can just find that one. So for part 3, we use QW plus QB plus QCU is 0. We know these guys. We just need to find an expression for the heat capacity of the copper. So let's use the fact that that is, well, again, this copper cylinder is not changing phase. It starts out as a solid and then remains a solid. So all we have to worry about is its heat given by its temperature changes, which is just given by the very similar formula as the previous one. However, its initial temperature we don't know. So its final temperature, the entire thing here is at 100 degrees. Its final temperature is 100. But it did not start out at 20. That's what we're looking for. So I'm just going to call that Ti, Cu. And that's what we're looking for in this problem. We have Tf as 100. We have the mass. We have the heat capacity of copper again, is the same thing right here. And we have these two quantities. So if you just plug this in here and then solve for the missing quantity, which is the missing temperature, that gives you that the initial temperature of the copper must have been 873 degrees Celsius. Now you want to make sure, just on physical grounds, that this value is below its melting point. If you get a number that was 873 but it melts at 500 degrees, that doesn't make sense because you didn't account for its phase change in the heat here. The copper melting point is actually much bigger than this, so we're fine here. And you see that it has to be pretty hot to get this guy to heat up to 100 degrees. So you put this very small copper cylinder in here, and because it's so hot, that heat, everything is isolated, that heat transfers to the water into the copper bowl, and then everything eventually equilibrates to 100 degrees. So that's that for the problem. Notice that to solve this, we always kind of start out with this formula. All the heats have to add up to 0 as long as the system is isolated. And then from there, you use the formula for heat capacity and the formula for the latent heat. Accounting for phase changes and for temperature changes, you should be able to find missing quantities. I'll stop there. Go ahead and take a look at the summary, and we'll see you next time.